going to be the first of a couple videos on infrared or IR spectroscopy. Many types of spectroscopy, including IR spectroscopy, involve the interaction between matter and light, or electromagnetic radiation. Light can be thought of behaving as waves or as packets of energy that we call photons. Two important properties of electromagnetic radiation are the frequency and the wavelength. We use the Greek letter nu to represent the frequency and the Greek letter lambda to represent the wavelength. I'm showing these equations just to try to tie this back to what you learned in general chemistry, but we're not actually going to do any calculations involving electromagnetic radiation. Our study of spectroscopy is going to be more qualitative. But it is helpful to remember that frequency is directly proportional to energy, and wavelength is inversely proportional to the energy. Infrared or IR spectroscopy specifically deals with the interaction between infrared radiation and molecules. And so here we have the electromagnetic spectrum. We have gamma rays on the short wavelength high energy side, and microwaves are the long wavelength low energy side. And so infrared is lower in energy and longer in wavelength than visible light. Different types of electromagnetic radiation interacts with molecules differently and provides the basis for different types of spectroscopy, which gives us different information about the molecules. This table just lists some of the types of spectroscopy that you've either used in the past or you're getting ready to use in this course. So in the next chapter, we'll talk about NMR spectroscopy, and that involves radio waves. The next couple of videos are about infrared spectroscopy, and infrared spectroscopy causes molecules to increase their vibrational energy. And then in general chemistry, you used UV-Vis spectroscopy, and that type of spectroscopy causes electrons to move into different orbitals. But of course, this video is going to be specifically about infrared spectroscopy. So as I mentioned on the last slide, when molecules absorb infrared radiation, it increases their vibrational energy. And molecules can vibrate in a variety of ways. So we can have stretches, where we imagine two atoms. We can sort of think about the bond as being like a spring, and so the atoms sort of move back and forth like a stretching spring. We can have bending motions, and we can also have sort of out-of-plane rotations or twistings. The signals in IR spectroscopy that we're going to be most interested in our study is going to be these stretching vibrations. And so when we're looking at IR spectroscopy, we're seeing molecules absorb infrared radiation to increase the stretching vibrations in the molecules. So part of what makes IR spectroscopy useful is that specific bonds can only absorb electromagnetic radiation with specific energies. And different bonds absorb different energy or frequency wavelength. And so a CH bond, the energy required to excite that vibration, is different than the energy required to excite, for example, a CO bond. And so which wavelengths of electromagnetic radiation that a molecule absorbs can tell us about what types of bonds are or are not present in that molecule. So this is a simple schematic for how an IR spectrometer works. So generally we have a light source where the light being emitted is sort of all wavelengths of infrared radiation. And then that electromagnetic radiation is passed through a monochromator that selects just a single wavelength. And so we have one wavelength of electromagnetic radiation coming out of the monochromator, and we know its intensity or its brightness. We then pass that electromagnetic radiation through our sample, and the intensity of the electromagnetic radiation coming out of the sample is going to be decreased if the molecules absorb that frequency of radiation, or it will be unchanged if it doesn't absorb that. And then we have a detector that measures the intensity of the electromagnetic radiation coming out of the sample. And so if the intensity is higher when it goes in and lower when it comes out, then we know that the molecules have absorbed that specific frequency of electromagnetic radiation. And so then what the monochromator does is it scans through all of the different frequencies, and then we measure which frequencies it does and does not absorb. So this is pretty typical of what an IR spectrum looks like. And we often plot these as a percent transmittance. So at 100% transmittance, all of the light is getting through, and the molecules aren't absorbing light of that frequency. When we have these dips, these are what we call the peaks. And when we have peaks, that's telling us that the molecule is absorbing that frequency of radiation. All right, so the units on the x-axis of the IR spectrum are in wave numbers. And a wave number is just an inverse wavelength. And so the units are actually inverse length units, and we usually use centimeters. So the units are inverse centimeters. And the typical values that we see in an IR spectrum are between 400 or lower wave numbers up to about 4,000 wave numbers. And so again, these peaks indicate that the molecules are absorbing that frequency of radiation. When the percent transmittance is high, it means it's not absorbing those frequencies of electromagnetic radiation. So these peaks or absorption bands have three important characteristics that we're interested in. So one, what is the wave numbers or the frequency, right? Where does that peak appear on the x-axis? Another thing that we're interested in is the intensity, right? So that's how deep the peak is. So I would say that these two peaks have a high intensity, where something like this peak has a low intensity. And then we're also interested in the shape of the peak, right? So you can see this peak is very broad, where something like this peak is very narrow. And so the wave number, where it is on the x-axis, how deep the peak is, the intensity, and then the shape of the peaks are all important when we're interpreting an IR spectrum. And the next video takes a look at each of these characteristics in a little bit more detail.